Hi everyone, welcome to the Advanced Locomotion Series in Unreal Engine 5 and C++. In this series, you will learn how to create an advanced locomotion system in Unreal Engine 5 using primarily C++ and some blueprints. We will cover a wide range of topics, starting from the basics and moving on to more advanced subjects such as turn-in-place, leaning, and more. You will learn tons of stuff, including character movement, blend spaces, enhanced input, animation curves, and much more. However, this isn't a simple series. I expect you to have some experience with Unreal Engine and a good understanding of C++. Without further ado, let's get started. In this episode, we will begin by setting up the project, creating character movement functionality, and finally downloading a character mesh from the Epic Marketplace. Open the Epic Launcher and launch the Unreal Engine. I will be using the newest version 5.4. You can click here to download this version, or you can use any version you prefer. Let's create our project. In the Unreal Project browser, select Games. Here we have multiple templates to start with, but since we want to do everything from scratch, we'll keep it blank. Select C++, rename your project, and hit Create. The project has been created, and a new C++ project has been loaded in Visual Studio. In the Solution Explorer, select the project under Games. In the Source folder, you will see that Unreal Engine has created some initial classes. When we created this project, Unreal Engine generated a default map for us. However, it's not currently saved. As you can see at the top, it says Entitled. In the Content browser, let's create a folder to keep all of our maps organized. Now hit Ctrl+S, rename the map to anything you want, and save it in the Maps folder. I always give each folder a different color for easier and quicker recognition. Now let's start creating our character. We'll create a new C++ file of type character. At the top bar, select Tools, click New C++ class. We will select Character as the base class. Rename it to anything you prefer. I will call it Main Character. Finally, hit Create. We chose the Character class as the base for our character because it provides all the necessary functionality for a third-person controller. Characters are pawns that have a mesh, collision, and built-in movement logic. They are designed for a vertically oriented player representation that can walk, jump, fly, and swim through the world using character movement component. Once the code finishes compiling, you should see a new folder called C++ classes in the content browser, with a child folder named after your project. Inside this folder, you will find the character class we created. Let's create a blueprint based on the main character class we just created. Select the main character class, right-click, select Create Blueprint Class based on main character. Prefix the name with BP_ to indicate this is the blueprint of the C++ main character class. For now, just save the blueprint and close it. We will come back to it later. To keep our folders organized, let's create a new folder called Blueprints and move the main character blueprint to it. It also appears that I didn't save the map in the Maps folder, so I'll move it there. I can't move the map to the Maps folder. I'm not sure about the cause of this issue. Every time I click OK, the engine crashes. If this happens to you, try copying the map to the Maps folder. After successfully copying the map, delete the old map from its original location. Before we start writing the character movement code, let's create a game mode. In the world settings, you'll notice that we don't have a game mode yet. At this stage, we only need a game mode to set the default pawn class, which will be our main character, so it will be spawned once the game runs. Select Game Mode Base, rename it to anything you want, and hit Create. Now let's create a blueprint based on the main game mode base class we created, similar to how we created the blueprint for the character class. Let's dock the main game mode blueprint at the top and keep it open. In the Details panel, under the Classes section, locate the default pawn class, set it to the blueprint version of the main character. Then compile, save, and close the main game mode blueprint. In the World settings, let's set the game mode override to our custom game mode. This ensures that our main character will be spawned at the beginning of the game. Setting the game mode in the World settings will only apply to the current map. To set the default game mode for all maps unless specified otherwise in individual map settings, you can do this in the project settings. While we're in the project settings, we can also set the default map to our created main map. Hit Run to test if the game mode was set correctly. Press Shift plus F1 to eject, then click this icon to detach from the player controller. In the outliner, you should see that ABP_main character was successfully spawned. Great! Now let's open Visual Studio and start writing the character movement code. Open the main character.cpp file. Close all other tabs since we don't need them for now. To open the main character.h file, simply hit Ctrl and click on the class name. Let's organize the main character.h file a bit. First, let's move these two methods to the top public section with the constructor. Then let's add a private section for all of our private variables and functions. We'll keep the last public section for getters and setters, as well as for anything we want to expose to other classes. For a third-person controller, we need a camera to follow the character. We want to place this camera behind the character at a distance. Unreal Engine provides the spring arm component, which is perfect for this purpose. The spring arm component tries to maintain its children at a fixed distance from the parent. In our case, the camera will be the child. Basically, we will use the spring arm component to pull our camera backward by a specified offset. We will call it the camera boom. The spring arm component also handles collisions with the environment, ensuring the camera doesn't clip through walls or other objects. Now that we understand what we need, let's start by creating the spring arm component to position the camera. Since this is going to be a pointer, we will initialize it to null pointer by default. If you're wondering why we create components as pointers instead of simple data types, there are several reasons. In Unreal Engine, components such as uSpringArm component and uCamera component are declared as pointers due to dynamic memory allocation and component management. Components are often created using functions like createDefaultSubObject, as we will see together shortly, which return pointers. Managing components through pointers is consistent with Unreal's architecture, and many other reasons we won't get into in this tutorial. Visual Studio doesn't recognize the SpringArm component class because we haven't included the header file for it. However, since we don't plan on using any functionality of the SpringArm component class in the main character.h file, we can forward declare it. This tells the compiler that there is a class called uSpringArm component. Then in the .cpp file, when we create this component, we will include the header file. To make the camera boom variable visible within the Unreal Engine editor, we will use the uProperty macro. We want this variable to be visible anywhere in Blueprint read-only, and we'll categorize it under camera. Since this variable is declared as private, it won't show in the editor by default. To make it visible, we need to set the metaPrivate allow access to true in the uProperty macro. This ensures that this variable can be accessed in the editor despite being private member of the class. Let's now create the camera component. We will use the same uProperty macro of the uSpringArm component. The Visual Studio says we should not use blueprint read-only on private variables. Actually, this is correct, but since we use the meta specifier, it should be fine. However, let's remove it because the visible anywhere specifier alone is sufficient to make the property visible and editable in the details panel of the editor. In the constructor, we'll create the camera boom using the create default subobject templated function. We'll use the text macro to assign it a name. This name will show in the editor. We will see that shortly when we open the editor. Next, we'll attach the camera boom to the root component. Since our main character class inherits from the character class, the root component by default is a capsule component, which is responsible for collision detection. This capsule also includes other child components such as the arrow component indicating the forward direction and the mesh component, which we will visit shortly when selecting a character mesh. The capsule component being the root means we'll attach the camera boom as its child. We can't access any function on the camera boom because now we must include the header file for the spring arm component. It's really hard to remember all the header files for the different components, so what we can do since we know that we need the header file for the spring arm component, we can simply search for it in the Solution Explorer, and once we find it, we can select it and open the Properties window, which shows the path, and then we can extract the header file. I personally don't use this method too often. I prefer visiting the Unreal Engine C++ documentation and get the header from there. Let's visit the documentation together and see how we can quickly get the header file for the spring arm in the camera component. This is the Unreal Engine C++ documentation. I will leave the link for it in the description. You can select the engine version here. Scroll down and you will see the Classes section. Click on it. The classes are organized in alphabetical order, which is really nice. But if we were to look for it, would still take some time, so simply hit Ctrl plus F1 to search for the component you need to find the header for. Camera component, for example, here it is. Just click on it, scroll down and you will find the header under references. Let's copy it and paste it into the code. Now you can do the same thing for the spring arm component. Now we can access the setup attachment function on the camera boom to attach the camera boom to the root component. We have access to the root component through the getter function getRootComponent. Let's proceed to create the camera component and attach it as a child to the camera boom. The camera boom provides a socket name, which serves as the endpoint for attaching the camera component. We can access the socket name directly from the uSpringArm component class since it's declared as static. Let's configure the camera boom settings. To rotate the spring arm based on the player's controller, we'll set the BUsePawn control rotation flag to true. For the camera, we want to set the flag BUsePawn control rotation to false, because we don't want the camera to rotate relative to the spring arm. Let's also set the target arm length on the camera boom. The target arm length variable determines the distance behind the player where the camera will be positioned. A value like 350 units is a good starting point, and it can be adjusted later if needed. Compile the code and then return to the editor. I will disable live coding and compile the code directly from Unreal Engine using the compile button. However, if the in-editor compilation doesn't work properly, you can compile the code from Visual Studio and then reopen the editor from Visual Studio. Great, the code was successfully compiled. Open the main character blueprint. You can see the camera boom was created and attached to the capsule component, and the camera is a child of the camera boom. In the viewport, you can see the camera boom indicated by the red line, which is distance from the character by the distance specified in the code determined by the target arm length, and the camera is attached at the end point of the spring arm. Let's hit run to see if everything is okay. Actually, let's first make the capsule visible in the game since we don't have a character mesh yet. In the Details panel, search for the hidden in-game flag and set it to false. After that, hit run to see the results so far. Great, the camera is positioned behind the character just as we specified in the code. Now let's start working on the movement code. At this point, we want the character to move forward, backward, left, and right for basic movement functionality. To do so, we need to find a forward direction vector and a right direction vector so the character can walk in the direction the player is facing. However, we can't simply use the forward vector and the right vector of the world. The player will be using the mouse to rotate in all directions, and therefore the character would have to move in the direction of the controller, so we have to calculate a forward and right direction vectors based on the rotation of the player controller. If you don't know what a controller is an actor responsible for controlling a pawn or character. Each pawn or character spawned in the game, an actor called player controller will be spawned with each human player to possess it and control its actions. The player controller manages input from a player, such as a keyboard, mouse, or gamepad. It is responsible for handling player input and translating it into actions for the character or pawn. There is also an AI controller that manages AI-controlled characters or pawns. It handles behavior and decision-making for non-player characters and PCs. The controller has a property called control rotation, which typically represents the direction the player is looking at or the orientation the AI is facing. In the case of a player controller, control rotation is often linked to the camera's orientation, which is exactly what we need. This allows us to create forward and right direction vectors based on this rotation. So when a player rotates the camera using the mouse or a gamepad, the control rotation changes accordingly. This rotation is then used to calculate movement direction vectors so the character moves in the direction the player is looking at. After all that, I think we now understand better what a controller is. Let's head back to Visual Studio to work on the movement. We need two functions, one for handling forward movement and another for handling right movement. We will place these functions in the protected section. Each function will have a parameter named value, which represents the input value from the user, such as from the keyboard. This value ranges from -1 to +1, where negative values indicate the player intends to move backward, and positive values indicate the player intends to move forward. If the value is 0, it means the player is not pressing any input, and therefore the character should not move in the game. Let's create definitions for both functions. Instead of doing this manually, we can let Visual Studio handle it for us. Select both functions, click the Quick Actions tool, the light bulb icon on the left, and then select Create Definition from the menu. Control-click on any of the functions to navigate to their definition. Let's begin by verifying if there is no controller, which we can access using the getController function. Additionally, check if the value is 0. If either condition is met, perform an early return. As we discussed earlier regarding controllers in Unreal Engine, the controller has a control rotation. We want to use this rotation to determine the forward and right directions. To do this, let's start by obtaining a reference to the control rotation. The controller has a function called getControlRotation that returns an f-rotator. We use the const keyword since we are only obtaining this value, not changing it. We don't need the rotation on all axes. We only care about the y-axis, which represents the rotation to the left and right. The next step is to calculate the forward direction. Using the obtained rotation, we can create a rotation matrix. This matrix will provide us with the unit axis aligned with the rotation value. A unit axis has a length of 1, indicating direction. Specifically, we are interested in the forward direction, which corresponds to the x-axis. Finally, we will invoke the addMovementInput method, providing the forward direction we calculated and the value parameter received from the user's input. Now we can duplicate all of this for the moveRight function, with the only change being the unit axis being the y-axis, which corresponds to the right direction. Let's also rename the direction vector to right direction instead of forward direction. Let's now connect some inputs and test this in the editor. Scroll down to the Setup Player Input Component function. Here we can add all the input bindings, using the player input component pointer to bind axes and actions. In this episode, we will add inputs using the old input system. However, in the next episode, we'll implement the enhanced input system, which offers more advanced features. With enhanced input, we can dynamically add and remove mapping contexts for the player at runtime, among other useful capabilities. In the editor, open the project settings and scroll down until you find the input section. As shown at the top, Unreal Engine recommends using enhanced input, which we'll implement in the next episode. For now, let's continue using the traditional axis and action mappings. We need to set up two axes, one named Move Forward and the other Move Right. We'll use the WSD keys for movement. For Move Forward, we'll set the scale value to -1 for backward movement, corresponding to the S key on the keyboard. Similarly, for Move Right, the scale value for the key will be set to -1 to indicate movement to the left. We can also include gamepad mappings. The input values from these devices, the keyboard and the gamepad, are between -1 and 1. This value is received in the value parameter within the Move Forward and Move Right functions in the main character class. While in the editor, let's compile the code to verify everything is working correctly. Next, in the Setup Player Input Component function, let's first ensure we have a valid player input component. If not, we can use a check assert to handle this scenario efficiently. Now we will use the bind axis method on the player input component to bind the axis mapping Move Forward to the Move Forward function we created earlier. The first parameter specifies the axis mapping name, which we call Move Forward. The second parameter asks for the object that owns the function to be bound, and since Move Forward is a member function of this class, we pass this, referring to the current instance of the main character class. Finally, we specify the address of the Move Forward function within the main character class, which is the function that will be called whenever the Move Forward axis input is received. Duplicate it and change the Move Forward to Move Right. Then compile the code and return to the editor to test it out. Before we hit run, let's make the capsule visible. This is just temporary, as we will add a character mesh after we finish writing all the movement code. Great! Now we can move the character in all directions using both keyboard and gamepad input devices. But currently, we can't rotate the character. So let's define inputs for both turning and looking up. First, we will define inputs for the turning axis mapping, which corresponds to rotating around the year axis, and then for the lookup axis mapping, which corresponds to rotating around the pitch axis. For the lookup axis, I'll set the scale to -1 since some people prefer the mouse y-axis to be inverted. You can experiment with both positive and negative scales to see what works best for your game. While we are in the project settings, let's add an action mapping for jumping. We only need an action mapping for jumping, since it is a simple press and release action. Let's also include gamepad mappings for turn and look up. In the main character.h file, create two functions, one for turning and another for looking up, each with a value parameter similar to the movement functions. While we could directly call it controller yaw input and add controller pitch input in the setup player input component function, defining these functions allows us to control the rotation rate more effectively, which we'll address shortly. Create definitions for both functions and navigate to the definitions in the main character.cpp file. First, let's add the same check we used in the movement functions. You can simply copy the check from the Move Right function and paste it into both the turn and lookup functions. Turning refers to rotating around the yaw axis, which can be achieved by calling the add controller yaw input and passing in the value. This method works seamlessly for mouse input. However, when using a gamepad stick, which is pressure sensitive, simply passing the value is insufficient. To control this more precisely, we should specify a rate, such as 50 units per second, which feels responsive but not too sensitive. You can experiment with different values in the editor to find what suits your game best. To ensure smooth gameplay across different frame rates, multiply the rate by delta time. Optionally, you can introduce a sensitivity variable for mouse input as well, though for now we'll leave it as is. The reason we typically don't need sensitivity adjustment for mouse input is because the mouse movement itself directly translates into a specific change in the yaw axis rotation. Unlike gamepad sticks, which vary in pressure and thus require sensitivity adjustments to control the rate of rotation accurately, mouse input provides a direct one-to-one relationship between the movement of the mouse and the rotation of the character. Therefore, applying additional sensitivity adjustments to mouse input might lead to unpredictable or exaggerated rotations, which can feel unnatural to players. I will be using the mouse for turning and looking up, so I will comment this line. Now we can do the same thing for looking up by using a controller pitch input instead. This will handle the pitch rotation for looking up and down. In the Setup Player Input component function, duplicate the bind axis line for move right, and change the axis name to turn, as well as the function name to turn. Do the same for the Lookup function. Adding jumping functionality is straightforward because the character class, which we inherited from, already includes a jump function to handle the jump mechanics. Since jumping is an action mapping, we need to use the bind action function instead of bind axis. It uses the same parameters, but the second parameter represents the input event state through the input event enum. For jumping, we want to use the IE_pressed input event. We can also define what should happen when the jump input is released. The character class includes a function called stop jumping, which we can call when the player releases the jump input. Now let's head back to the editor, compile the code, and hit run to test the results. Great! Now we can move freely in all directions and use the mouse or gamepad to look around. And we've also implemented jumping. Before we wrap up this video, let's head to the marketplace in the Epic Games launcher and download a character mesh. You can use any humanoid character you like, but in this tutorial, I'll be using a character from the Paragon assets provided by Epic. I highly recommend using one of these characters if you want to follow along, as they come with tens of animations that we will be using, including leaning, aim offset, and many more. I will use this character. I have already downloaded it, so I will now add it to the project. If your project doesn't appear in the list, click the flag to show all projects. Once the download completes, locate the folder for your chosen character in the content browser. Expand the folder, navigate to Characters, Heroes, Meshes, and find the main skeleton there. Next, open the main character blueprint and check the hidden in-game flag for the capsule component, as it is no longer needed. Select the mesh component, and in the Details panel, find the skeletal mesh asset field. Click on it, and choose the character mesh you downloaded. Additionally, the Paragon asset character includes various skins that you can select from. The character mesh isn't aligned correctly, so let's move it down on the Z-axis by -90 units to align it correctly with the capsule. For precise alignment, we can move it down by the value of the capsule's half height. The misalignment happens due to the pivot point of the mesh. Additionally, rotate the mesh by -90 degrees to face the forward direction. Remember that the arrow component indicates the forward direction. Great, everything looks good. One final adjustment I want to make is hiding the weapon temporarily. Since the weapon is part of the mesh and cannot be hidden directly, we'll create a transparent material and assign it to the weapon. This will effectively hide it while we focus on developing different locomotion mechanics. Later on, when we work on aiming mechanics, inverse kinematics for holding the weapon correctly, and blending aim offset animations, we can show the weapon. In the Details panel of the skeletal mesh asset, click on this icon to browse to the character skeleton. Open the skeleton asset where you'll find the material for the weapon. We will create a transparent material and assign it to the weapon temporarily. In the Content browser, create a new folder and name it Materials. Right-click, select Material, name it M_transparent, and open it. This is going to be very simple. Press 3 on the keyboard and left-click to create a color node. Connect it to the base color input. And now press 1 on the keyboard and left-click to create a float variable with a value of 0. Connect this to the opacity input. The opacity value is grayed out because by default the blend mode is set to opaque. In the Details panel, change the blend mode to translucent. This simple material will make the weapon transparent when we apply it to the weapon in the character skeleton, which will hide the weapon temporarily. Save the material, then open the character mesh's skeleton asset. Select the weapon bone and apply the newly created material to it. Great, that wraps up this episode. In the next one, we'll begin by implementing the enhanced input system. After that, we'll dive into the animation system, where we'll create an animation instance class in C++, add animations and blend spaces, and explore more features. Thank you for watching, and see you in the next episode.